We're continuing the discussion of electrons and where they exist in the atom. So in 1913, Niels Bohr, who was a Danish scientist, set down some postulates to account for things he was seeing in the hydrogen atom. So what we see here below is an emission spectrum, and each one of these colors that are emitted are a certain wavelength of the visible light spectrum, and we know that's electromagnetic radiation. And so these are actually similar to fingerprints. We call them the fingerprint of each element because each element will have a different emission spectrum. So when you see this purple, the blue line, the green line, and the red line, it is indicating that it is hydrogen. Now, the problem with this was Niels Bohr really only worked with hydrogen, so all of his postulates account really well for hydrogen's properties, but we do learn a little bit further in the years that this actually isn't applicable to many other elements because we know hydrogen is such a simple, small molecule. So this is then what Niels Bohr decided the atom looked like, and this is called the Bohr diagram, and we still actually use these today. He knew that there was a center nucleus, and that has a positive charge. We decided that from Ernest Rutherford's gold foil experiment. And then instead of the electrons just kind of being in random locations, Niels Bohr decided that they would be in orbits. Now, I do want to let you know we've converted that term now to be orbitals, which is a little bit different and something we'll talk about later on in this PowerPoint. But the term orbits, he was under the assumption that electrons would be kind of revolving, similar to how the planets revolve around the sun, in these different what we call subshells or sublevels or energy levels. So that is kind of still how we draw the atom today, but we've learned a little bit more about how it looks and how it acts. And he also learned that the color that we see from the emission spectrums are actually from the movement of electrons from what we call the ground state to the excited state, and then from the excited state back to the ground state. And all of this has to do with what we discussed before, photons. And remember, photons are little packets of light, packets of energy that come from the sun. So we're going to definitely discuss this in detail. I have a good photo on the next screen here, but we are going to be seeing that the electrons in their what we call ground state can absorb a photon or absorb a packet of energy, and then they can they'll have more energy, so therefore they kind of need to let it out, so they will move up to a higher energy level, and then when they come back down, the given off photon is what is going to create that sort of frequency, which then can be related to a wavelength, which then we can create a color on the electromagnetic spectrum. So again, most of this really only applies to hydrogen, but this does work with a lot of other atoms. It's just a lot more complicated. So the transition between, remember, energy levels, that term energy levels, we are going to also be calling energy shells. So each of these kind of rings around here are going to be called energy levels. And there's a lot of new terms in this chapter, so make sure you're kind of keeping those straight. But we're going to talk about how electrons move in the atom. So an electron can change energy levels, and those are the shells, by absorbing energy. And they absorb energy in the form of a photon. And then from that, so I actually have a really good diagram here below. So here we have the photon. Remember, they move as a particle and a wave. We call that the wave-particle duality. So they go ahead and they're absorbed by this first level electron. Now, without the energy being absorbed, we call this their ground state. When the photon is absorbed, they gain that energy from the photon and they move up. They could move 1 shell, 2 shells, 3 shells, 4 shells. Just depends on how much energy the photon gives off. And then up at that state, they call it the excited state. And this state is not very permanent. This is actually an instantaneous kind of jump, and then it will then jump back down. And the jumping back down from the excited to the ground state, giving off the photon, is when the actual wavelength of light is given off. So there's always a misconception. It is not this first process here where we see light being given off from an emission spectrum. It's actually this second process where the excited electron is being brought back down to its ground state, and this wavelength being given off is what produces the visible light that we see. Okay, so again, it's not when they move up to the excited state, it's when they move from the excited state back to the ground state and that photon is released. We can calculate a frequency, then we can convert that to a wavelength. We've talked about this a couple of times. Light has properties of both waves and particles. Einstein and Max Planck discovered that. And so we're going to go ahead and fast forward to 1923, and we have Louis de Broglie, and he was a French physicist that kind of put together a couple more equations relating wavelength, mass, velocity, and also that Planck's constant that we talked about prior. So this is an equation I will provide you on all exams, and it is, again, wavelength equals Max Planck's constant, which you would know to be 6.626 times 10 to the negative 34th joules seconds. And then we're going to go ahead and divide by m, which in this case is mass, and v in this case, which is velocity. So again, I want to remind you that the units need to be correct for this equation to work. So your mass has to be in kilograms, just like it has to be in the kinetic energy equation. And then velocity has to be in meters per second. And then the h we know to be in the joules second. And then with all these units coming together, when you convert, our wavelength ends up being in the required meters. Now, if you'd like to kind of work through that, how to cancel the units, I would have no problem doing that with you. Please let me know. In this video, I'm just going to go ahead and maybe have you use process of elimination to figure out what unit you need. We're going to go ahead and apply that equation that we just used to two examples here. So we're going to be comparing the wavelengths of a baseball and also of an electron. So go ahead and look. We are given masses in kilograms, which we know to be the correct unit. We are also given speed, or velocity, in meters per second, which is correct. So let's go ahead and try to set that up. If I were you, I'd try to set that up on your own, and then you can go ahead and check your work with mine. So I'm going to go ahead and reveal the A. So what I did here was take the Planck's constant, and again, you know you're going to be given that value, so you don't have to memorize that. And then I went ahead and divided by the provided mass in kilograms, and then the speed in meters per second. Now I want to remind you, when you're doing this math, please put parentheses around the numbers in the bottom as the denominator, because if you do these separate, you will get the incorrect answer. So please, as we're doing these videos, try these on your own calculator, because on a test you need to make sure you know what you're doing. So we're here provided with our wavelength in meters. Now we're going to go ahead and look at the other example. And we have the 6.626 times 10 to the negative 34th. And again, we provided our electron mass and velocity. And then we have another wavelength, and we're going to go ahead and compare. So the larger wavelength here is the electron, and remember our relationship between wavelength and frequency, which is inverse. As one increases, the other decreases. So I could ask a question like this, and then I could have you make an assumption about the frequency. So please make sure you understand those relationships. Now, classical physics wasn't sufficient enough to describe very, very small particles. We call those subatomic particles, and subatomic particles are protons, neutrons, electrons. So therefore, we have Mr. Schrödinger, and you may have heard of him, of course, with Schrödinger's cat. But this is a branch of physics that mathematically describes wave properties of very, very small subatomic particles, and this is a whole branch of science called quantum mechanics. This is something that is being studied still to this day, and we're learning so much more about the properties of these waves of very, very tiny particles. So quantum mechanics changes how we actually think about the motion of particles. And so we have Mr. Heisenberg in 1927. I'm hoping you're seeing there's a lot of research going on, in the early 1900s. But remember, these people are living in different countries, and they don't really have the communication method to kind of share their research. So a lot of things are contradicting things at the time, and eventually we end up getting a better picture of all the research together. But Mr. Heisenberg showed that it was impossible to know with absolute precision both the position and the speed. And we're going to actually learn this to be called the Heisenberg uncertainty principle, and this is a possible question you may see. So again, the Heisenberg uncertainty principle is that you can either know one or the other about an electron. You can either know the position or the location or the speed. You cannot know both at the same time. And this kind of contradicted Bohr's fundamental beliefs about electrons. All right, and the last thing we're going to look at here are orbitals. And remember, prior, Niels Bohr was calling them orbits, and so now we're going to use the term orbital, and this is kind of a confusing topic. So an orbital is the probability of finding an electron within a certain space. So instead of this being a very solid mass that we can kind of assume we'd find an electron, let's say I have a nucleus here and some subshells, instead we have to kind of imagine this as our first circle. And it's a density map, meaning the darker color means we have found electrons there more commonly than we have found electrons in the outer lighter colors. So instead of it being kind of stuck in a ring, it's basically anywhere along here, okay? And they are constantly moving. Remember Heisenberg uncertainty principle, we can't tell you either the precision or the speed, only one. So this is kind of adding to this idea. So instead of calling them orbits, we're now going to call each probable location of finding an electron an orbital. And when we get to